Hey there, and welcome. Today, we're going to dive into the world of mathematical logic. Now, I want you to think of it as the language of pure, absolute reason, a way to build arguments that are so solid they're basically unbreakable. And it all kicks off with one simple question. Seriously, think about that. A conversation with zero ambiguity. In our everyday lives, that's pretty much impossible, right? We use slang, our tone of voice, we rely on context, and that leads to a ton of confusion. But if you need to talk to something that doesn't get nuance, like a computer, well, you need a totally different kind of language. And that's exactly where we're going to start. We're building a language of absolute certainty. To get that kind of perfect clarity, we have to lay down some rules that are completely black and white. And here's the core idea, the big trade-off. The way we normally talk is flexible, it's creative, but man, is it messy. Logical language, on the other hand, is built for one thing: precision. It gives up all that flair, but what it gets in return is perfect clarity. And this whole system is built on one simple, really powerful idea. So, where do we even begin? Well, it all starts with the single most fundamental piece of the puzzle, the basic building block of all logic, something we call a statement. So here's the golden rule, the one thing that matters. A statement has to be a sentence that you can look at and say, without a doubt, that's true or that's false. There's no gray area, no maybe, no, well, it kind of depends. It's one or the other, period. Okay, let's look at some examples. This makes it super clear. On the left, the sun is hot. Is that true or false? It's true. So it's a statement. How about Mumbai is in Japan? That is definitively false. So, yep, it's a statement too. Even a wrong math problem like 5 plus 4 equals 13 is a perfect statement because we know for a fact that it's false. Now look at the right side. Do you like math? You can't say that's true or false. It's a question. Close the door. That's a command. Wow, what a view, is an exclamation. None of them fit the rule. So just to be crystal clear, these 4 types of sentences, they can never be logical statements. Commands, questions, exclamations, they're out. And you got to pay close attention to that last one, open sentences. Something like x plus 3 equals 5 isn't a statement yet because, well, we don't know what x is. If x is 2, then it's true. But if x is, say, 10, then it's false. Since its truth depends on a mystery variable, it's not definitively one or the other. Okay, so we've got our basic building blocks, these simple true or false statements. Now the fun part begins. How do we combine them to build more complex, more interesting ideas? We do it using these special tools called logical connectives. These are the 5 essential tools in our logic toolbox. You can think of them like the glue or the mortar that holds our statement bricks together. We've got and, or, not, if then, and if and only if. Now, to really get a handle on this, we're going to zoom in on the 2 biggest players in the group, the ones we use constantly, and or. All right, check this out. This is the official rulebook for and. An and statement is like a really strict parent. It's only happy, it's only true, if both of its parts, P and Q, are true. If even one of them is false, the whole thing falls apart and becomes false. No exceptions. But then you've got or, which is, way more laid back. An or statement is happy and true as long as at least one of its parts is true. If P is true, it's good. If Q is true, it's good. If they're both true, still good. The only possible way for an or statement to be false is if both parts are false. So with all these rules, how do we keep everything straight, especially when we start chaining these things together? Well, we use this absolutely essential tool for mapping out every single possibility, the truth table. The incredible thing about a truth table is that it's basically a cheat sheet for reality. It lets us map out every single outcome ahead of time. By just systematically going through every combo of true and false, we can know with 100% certainty how a complex statement will turn out. It just wipes away any doubt. All right, I know what some of you might be thinking. This is all very neat, very tidy, but what's the actual point? Well, this is where this abstract puzzle suddenly becomes very, very real. See, this whole system of true, false, and or, it's not just for some dusty old textbook. It is literally the fundamental blueprint for the technology that powers our entire modern world. And boom, this is where it all comes together. Think about a simple electrical circuit. The and rule we just talked about, that's a series circuit. You have 2 switches in a row.
For that light to turn on, switch P and switch Q must both be on. Now think about OR. That's a parallel circuit. The electricity has two paths it can take. The light will turn on if switch P is on or if switch Q is on. The abstract rules of logic perfectly physically describe how electricity behaves. And that right there is the whole game. True and false can be physically represented by on and off, or, as you've probably heard, by 1 and 0. And with those simple building blocks, connected by these simple rules of and or, you can build every single computer chip, every processor, every digital device on the face of the earth.
So that leaves us with this one last kind of mind-blowing thought. If the simple switches that run a light bulb are built on this pure, perfect foundation of logic, what about all the incredibly complex systems we use every single day? From the phone in your pocket to the giant algorithms that run our world, it all comes back to these simple, certain, and unbelievably powerful building blocks of reason.